let's apply everything that we talked about with molarity and dilutions, and let's apply this to stoichiometry. So there's a series of problems that we can use molarity for to help us solve some information in stoichiometry. The first type of problem is called gravimetric analysis. Okay, so gravimetric analysis, what this is this is an analytical technique that's based on the measurement of mass. Okay, and so this based on the measurement of mass, this is based on the formation, isolation, and mass determination of a precipitate. All right, so let me give you an example. So let's say you take silver nitrate and you react it with sodium chloride, and here's a reaction. AgNO3 plus NaCl yields NaNO3 plus AgCl solid, and silver chloride is your precipitate. Okay, if we write the net ionic equation, it's silver plus ion plus chloride ion yields silver 1 ion, silver 1 chloride. So let's say we wanted to know what was the percent by mass of chloride ion in the original sodium chloride solution. Okay, so what we'd have to do is make sure that sodium chloride is your limiting reagent, so that controls how much chloride ion you actually have. And what we're going to do is do this reaction, but make sure, because silver chloride is your precipitate, what we're going to do is isolate that silver chloride, dry it, weigh it, so that way we can figure out how much silver chloride was produced in the reaction, and then backtrack to figure out how much sodium chloride was added to make this reaction work. Now, gravimetric analysis is highly accurate because the mass of the sample can be measured accurately. Okay, and it all depends on how well your balance is calibrated and how well it's working. Now, the drawback, because it's highly accurate, is that we need the reaction to make sure that it goes to precipitation. So it goes all the way to completion. So you got to have 100 or almost 100% yield. All right. So let me give you an example of a gravimetric analysis problem. Let's try this out. So here's how the problem goes. A sample of 0.3220 grams of an ionic compound containing the bromide ion is dissolved in water and is treated with an excess of silver nitrate. Okay. If the mass of the AgBr precipitate that forms is 0.6964 grams, what is the percent by mass of bromine in the original compound? All right, so we got some work. So we know that we got a compound that contains some sort of ion, some sort of cation, but we know bromide is in there. Okay, and we react this with AgNO3, and there's a reaction that takes place. Now, because this is a double displacement reaction, X will replace the silver, and silver will replace the X. Okay, so that way one product is AgBr, which we know that that's the precipitate because that's what we're told in the problem, AgBr precipitate. The other product is going to be the cation X plus NO3. All right, and this is going to be aqueous. That's going to be still in solution. Now, do we need to know X for this problem? Nope. Doesn't matter to us because that's not what we're interested in. At the end of the day, we want to know in this compound, in this XBr compound, how much of this is Br. So what we're going to have to do is figure out how much bromine we have in this compound here, and then kind of use law of conservation of mass to help us out. So let's figure this out. So we were told that you had a mass of 0.3220 grams of this compound, XBr. Okay, And when you go through this reaction with AgNO3, you form 0.6964 grams of AgBr. So we want to know inside that AgBr compound how much of this 0.6964 grams is bromine. All right, so let's figure this out. The first thing we need to do, we're going to start with that 0.6964 grams of AgBr. We want to know how much bromine is in there. So the first thing we're going to do is convert this from grams to moles. Okay, so we're going to put 1 mole of AgBr on top. We're going to put the molar mass in the bottom. The molar mass is 187.77 grams of AgBr. So that way grams of AgBr cancel out. We're in moles of AgBr. So now we need to figure out how many moles of bromide ion we have in 1 mole of AgBr. So you need one, since you're making one mole of AgBr, you're going to need 1 mole of bromide ion to make 1 mole of AgBr. So the way I'm going to write this, on the bottom I'm going to put 1 mole of AgBr. So for every mole of that, we're going to have 1 mole of bromide ion, of Br minus. All right, so moles of AgBr cancel out. What we want to know, though, is how many grams of bromide ion we actually have. So now what I'm going to do is convert this from moles to grams. We use the periodic table for that. So on the bottom, I'm going to say 1 mole of Br minus. On the top, the molar mass of bromide ion is 79.90 grams of Br minus. So that gets us back to grams of Br minus. All right. So math-wise, this is going to be 0.6964 times 79.90 divided by 187.77. So this should come out to be 0.2963 grams of bromide ion. So out of that 0.6964 grams, we know that this much, 0.2963 grams, has to be bromide ion. Okay. So now here's the question, here's what we're asking for. In this original compound over here with this cation that we don't know plus bromide, how much of that contains bromine? Well, if we use the law of conservation of mass, if we have 0.2963 grams of bromine or bromide ion in the products, that's how much we have in the reactants. Okay, so what I'm going to do is take the 0.2963 grams of bromide ion, and let's divide it by the mass of that compound, 0.3220 grams of XBr. And if we take that number and then multiply it by 100%, that'll give us what is the percentage of bromine in that original compound. So if you take those two numbers divided and multiply it by 100, the number comes out to be 92.02%.